Welcome to the first installment of The Physics Dudes! Today, we will talk about Galilean relativity and frames of reference. Here with me is my associate, Dr. Olakwi.
So, what is exactly Galilean relativity, Dr. Super Evil Genius Alley?
I thought you were a doctor. Anyways, Galilean relativity, also known as Galilean invariance, is a statement that describes all the laws of motion to be the same in an inertial frame of reference.
Speaking of frames of reference, for those who are unaware, a frame of reference is a small portion of the physical world, which is defined by an observer, where the position and the motion can be described or compared.
Simply put, a frame of reference is something that one can use to describe an object's motion relative to some fixed object. The Earth is a common frame of reference since it seems to be fixed, and that is how we describe the motion of cars or planes relative to some fixed point on the Earth. Well, earlier we did an experiment which demonstrates the idea of frame of reference. I will hand it over to Dr. Murphy, who will elaborate on this experiment.
This experiment uses highly advanced equipment, so kids, don't try this at home. In that experiment, you had an overhead view over the puck. You can assume the puck was moving because you could see the grid lines move behind it. In this frame of reference, you use the grid lines as a fixed point in order to determine the puck's motion. But what is really happening? This is the Earth's frame of reference since the camera is fixed to the counter, which is fixed to the building and to the Earth. In this reference frame, you could use the fixed counter to determine the object's motion to be at rest, relative to the counter or the Earth.
In both frames of reference, the puck was in uniform motion. This relates back to our original topic. Inertial frames of reference. A frame of reference where it is at rest or in uniform motion, but they are not accelerating.
Now, this relates back to Galilean relativity, which refers to frames of reference where the first two Newtonian laws apply. So guys, please leave a comment in the comment section below.
And subscribe and like the video. And we'll see you next time on
The Physics Dudes!
Here we see an air puck on a low friction surface. As there is no net force acting on the puck, it will move at a constant velocity, depicting uniform motion. This is the law of inertia. Notice that when the puck is moving back and forth, only the direction changes and not the speed.
In the other frames of reference, we can only see the puck moving, making it seem as if the surface it was on was still. This was not the case. In our new frame of reference, we can now see that both the surface and the puck are moving with uniform motion. When the cart and the puck are both moving forwards, it seems as if the puck is moving faster than when the puck and the cart are moving in opposite directions.
When the cart and the puck are both moving forwards, the actual velocity of the puck can be expressed as u plus v. U being the velocity of the cart and v being the velocity of the puck. Similarly, when the puck and the cart are moving in opposite directions, the actual velocity of the puck can be expressed as u minus v. So as you can see, the perceived speed of an object is all relative. It really depends on your frame of reference.
As you were watching the lion, you probably thought that he was moving on his own, until you realized that it was actually the background moving and not the lion. Let's take another look. This time, it was the lion moving. This shows that all motion is relative. The reason why we think that the lion was moving the first time was because our frame of reference was different from the lion's frame of reference. Galileo Galilei was an Italian physicist, and he hypothesized that objects will move at constant speed in a straight line with respect to a set reference point, which determines an object's motion. In accordance with Newton's first law, if the object is at rest or traveling at constant velocity, it will remain at rest or in motion. Galilean relativity states that the laws of physics are the same in all inertial frames of reference, meaning that the laws of physics are the same in different points of view that are moving at constant speed or at rest. Let's take a look at another scenario. A student is throwing a ball up and down while sitting on a chair and being pulled by her friend at constant velocity. From a stationary observer's point of view, the ball is moving in a parabolic shape. From the point of view of the student throwing the ball and the student pulling, the ball is not moving in a parabolic shape, but in a straight line up and down. As you can see, the movement of the ball is different at varying frames of reference. From a non-moving frame of reference, the ball forms a parabolic shape, and from a moving frame of reference, the ball is simply moving in a straight line. Remember that inertia is only referring to constant velocity or at rest, not acceleration.
So for our frames of reference project, we will be analyzing Galilean relativity and the respective frames of reference of our experiment. Our model consists of an upright cannon on a frictionless cart, which, with the release of a string, launches a metal ball upwards in front of varying frames of reference.
But first, what is a frame of reference? The textbook defines it as the subset of the physical world defined by an observer, in which positions or motions can be discussed or compared. Essentially, it's the way you observe a certain situation relative to your surroundings and environment.
Now onto our experiment. For the first two clips we are about to show, we have the cannon on a frictionless cart attached to another car with the camera, both moving at a constant velocity. The other clip features the cannon cart and camera totally still, and motionless. This is an inertial frame of reference for both clips, meaning no acceleration. See if you can spot the difference between the two.
The difference is nearly impossible to tell. We cannot differentiate between the two clips due to the fact that there is no discernible reference point, thus there is nothing to tell us whether the cart is moving or not.
Our next clip will show you another frame of reference. This perspective will allow you to observe the motion of the cart. Be sure to keep your eyes on the trajectory of the ball. As you observed in the clip, and as I'll show you in this diagram, it's clear to see this time that the ball travels in a parabolic trajectory rather than simply up and down. This is due to a different frame of reference, one where we're not traveling at the same relative velocity as the cannon cart. This time, we will alter the frame of reference by tracing lines on the backboard behind the cart. This will allow us to immediately notice whether or not the cart is in motion.
Interesting. This new frame of reference allows us to very easily determine whether or not the cart is in motion, as we now have the lines at the back to gauge the cart's movement. The first clip clearly showed that neither cannon cart nor backboard are moving, due to our frame of reference.
So, the second clip. The cart was moving because we saw the lines moving, right? Or wait, was the wall behind it simply moving backwards, with the cannon cart staying still? The point is that all motion is relative. We tend to associate one thing with being fixed, with another thing being in movement. But when we do that, it's impossible to truly tell if, for example, the cart is moving, or if it's the wall behind it. It's all dependent on your frame of reference.
The purpose of our experiment is comparing the path of a ball launched out of a cannon attached to a cart moving at a constant speed versus when it is accelerating. We will show how frames of reference affect how we see the path of the ball when it falls.
The cannon and the ball are both moving at constant motion. The camera is at rest. When the cannon launches the ball, due to its inertia, which is its resistance to changes in motion, the ball stays at a constant speed, as does the cannon. The ball lands back into the cannon because they maintain the same uniform motion. In this clip, the cart is still moving with a constant motion, but now the camera is attached to the cart. The only change is the frame of reference. In the Earth frame of reference, the path of the ball appears to be a parabola. However, from the still frame of reference, the ball falls down in a vertical path. The change in the path we see depends on the frame of reference.
The cart is accelerating and the camera is at rest. The cannon and ball are both accelerating. The camera is at rest. When the cannon is accelerated and the ball is launched, the ball, due to its inertia, maintains the speed it was launched at, also known as instantaneous speed. The cannon, which is still attached to the force causing it to accelerate, will continue to accelerate. When the ball comes back down, it and the cannon will now be moving at different speeds, which is why the ball does not land back into the cannon. The cart and the camera are accelerating together. In this clip, the cart is still accelerating, but now the camera is attached to it. The only change is again the frame of reference. When the camera is in an inertial frame of reference, at rest, the ball appears to be moving forward. In this non-inertial frame of reference, with the camera accelerating as well, the ball seems to be moving backward as it falls towards the track. There is the appearance of an unbalanced force acting on it, a fictitious force. It appears that the path of the ball was deviated from its vertical path because of this fictitious force.